Hmm. Alrighty then. The thing has been hit. It says we're live. Hopefully, we're actually broadcasting audio because all I know is I'm sure there's absolutely nothing affecting any of my AirPods. It's not like it. Different rant for a different time, but hey guys, what's going on? Memes here. And so over the weekend, apparently, Dr. Unzicker had attended, was it the conference in Munich, known as the Physical and Mathematical Ontology Conference. Um, so he gave a talk over there about gravity and everything, and went over to a bunch of things. And what I found fascinating is, let's just go over. So we got Doctor's presentation over here. Was that I started to notice something, and he had brought this up before, and we did a video that was interesting, and I'm may or may not have emailed the good doctor pointing something out, and there may or may not have been a short video saying that to caution what may have been said, but then I noticed this. I'm like, wait a second, okay, we've got our little h Planck's constant there. All right, we've got a pi divided by 2, and basically it's the mass of the proton, the radius of the proton. Okay, and then the speed of light in there. Okay. So the interesting thing is, if you do that, you get basically Planck's constant to like, I don't know, like 3 significant digits or something like that. Now, what we had noticed is just going to Wolfram Alpha, if you do something like this, and should we... We'll get to it in a second, just because I'm sharing the audio from this. But basically, if rather than taking the standard measured radius of the proton, which is right now it's about 8.4 femtometers, which surprised a lot of folks because it used to, at least according to some measurements, was about 8.7 femtometers. So it seemed to get a wee bit smaller in there. So hey, as we measure really little things better and better, hey, oh my God, we could be wrong about some things, or we at least become more accurate. That's the goal. So the interesting thing about this is, if you happen to use the classical radius, which, if I think it was Physics Explained, actually had an excellent video about this recently, about how scientists at one point were like, what's the electron? What if we literally just quantized it and we just said it was the strength of the electric charge for a given field area? What might happen? And basically, that, long story short, is that's how you get the classical electron radius. It's basically quantifying it as an amount of charge. Now, the interesting thing is, if you basically divide by about 137, aka you're dividing by or multiplying it, so to speak, by the fine structure constant, you coincidentally go down to what the average, excuse me, what within the error bars of the current best measured value of the proton is in here. As we can see, oh, okay, so this is basically like the first like 5 days. That's supposed to be, I think, a period there rather than a comma. But as you can see, it's just because it's the inverse of fine structure constant is 137.35999, and then we argue about the 10th decimal place. So 0.036 is pretty dang close for at least getting the first couple of significant digits. Okay. So as you can see, when he does this, he goes over here, and he starts playing around with it a little bit more. He's like, all right, what happens if we do this to the mass of the electron? So basically, he's incorporating Dirac's large number hypothesis here. I think this is great. I think this is fantastic for people to be playing around. Now, I am also very biased. And again, one of the questions that Dr. Unzicker does get in here is, well, okay, that lines up, but that's based upon the mass of the observable universe. There's still stuff up there that we haven't observed, which, to be fair, is an interesting thing. I saw another paper where it's like, all right, basically you take the, what is it, like, the Hubble radius or whatnot, or basically the radius of the observable universe. You cube it because that's a distance or a length there. So now you're getting a volume because it's a cubic. So you get a volume there. then you divide it by the mass of the observable universe, and then the the age of the universe squared within the denominator as well. So actually, let's just do this. I got a whiteboard right here. I might as well use it. So, all right, so let's just erase this real quick. Just show. All right. That's my arbitrary night scribblings where I'm just like, wait a second. All right. So basically, if you were to take, let's say big R, because it's the universe. R sub u, cube that. Now, you got a length. You square it, you're literally getting a square area. You cube it, you get you're literally getting your little cubic area right there, or volume, because we want to use the right terminology, right? And you have the, say, mass of the universe, and then you what's the age of the universe. So we'll do big T. Okay, that's, I know this is very confusing. Time universe squared, because and this is approximately gives you basically big G, which is a very interesting thing. It could be very suspect there. Maybe that's just a coincidence, but I don't know. Is that why it lines up with a proton? I don't know. I'm very biased. Personally, I think the universe, so to speak, is much larger. Now, I tend to be of the mind that the maximum extendability, that's about 10 to the 34 meters, about 100 million times larger than our current observable universe. Is that the state we're in? It depends on the calculation. Because I've done calculations, it's like, okay, I got stuff to work, but then the problem is, it's like, it's a dang dark energy. If you're going to take that as literal part of the quote-unquote mass bank of universe, so to speak, maybe we're only, I don't know, 1,000 or so times larger. I mean, that would be very fascinating right there. I don't know. It depends on if the cosmological constant, so to speak, is constant, or if it's just varying. Because I have explanations for both, but I'm like, that's going to make a very large difference. About 5 orders of magnitude. So I'm just being open and transparent best we can. So we'll go back to the video. Hey, Sandro, good to see you, my friend. Good to see you, my friend. It's man, I feel like I've been all over the place. I remember I talked with Sandro and I was getting ready to leave the monastery, and well, it's okay. Well, Rick is hailing from the great state of Washington, not the state of urine. It's good to know. Good to know. Welcome, Kali. I think I was just adding you into the Wolfram paper for some acknowledgments, because I'm like, yeah, no, Kali did have some influence on this paper, so I'll need to get that updated there. All right, so let's go back into the good doctor's talk. So zoom out a little bit. But long story short, here I'm like, wait a second. Weren't we talking about something about alpha, the fine structure constant? If you add it into your little equation for the proton here, you can basically, hold on, we'll just do that just because we're right here right now. All right, so go back to our friend. Okay. Boom. Okay, so basically, what Dr. Unzicker did is he's got like pi divided by 2 gives you that factor there. Okay. Then he takes c, the speed of light. He takes the proton mass, and then you multiply by the proton radius. Let me see. Okay. So as you can see, it gives you like, gives you at least the first couple of digits of Planck's constant. I mean, that's pretty cool there. See, for me, I'm a noob and the simple type of guy, so I'm just like, let's just take that pi over 2 term that we inserted off. What do we got? Okay. Oh. See, it just changed everything. All right, so that's why we need to do the speed of light. Speed of light. It interprets it different because it's like, you're talking about particle stuff, so we're going to throw the charm quark in there. All right. So we're assuming multiplication. What happens? Okay. So, all right, we're using this thing. All right, so it's like 4 off. Okay, we could just use that. And what's this? Classical proton radius. Oh, let's just click on that. Gives you this number, and you're like, all right, there's a bunch of joule seconds. I don't know what that number means. Bada boom, bada bang. Oh, what's this? Oh, our numerical result appears to be about 1/137th of h bar, Planck's reduced constant. So of course, you're like, oh, what happens if I do multiply by the fine structure constant? Multiplication, because there's a whole lot of different stuff there that might not always be associated. What do we do? We needed to divide, didn't we? Okay, sorry. Noob. Multiplication. Oh, wait. Sorry. Boom. Classical proton radius. Derp. See? It reassigned it. And now we divide by alpha. Sorry. I'm all over the place. This guy don't know what he's doing. It's not necessarily the worst thing. Here we go. Okay, what's this? Now we've done it right. Now we have the speed of light times the mass of the proton. And then the classical radius of the proton, and we just divide by the fine structure constant in there. Okay. So give us there. Well, this seems to be Planck's reduced constant, and that goes for 9 significant digits. Those last digits should be like 1, 7. Let's just do this. Bracket the whole dang thing. Divide by h bar. Gonna have to click our little thingies again. Boom, boom. Oh, look, 1. It rounded in the 9th significant digit. So it should technically be 1, 7, but it rounded to 2 because, well, there was only so much information. But I don't know. I'm sure this discussion had nothing to do with the good doctor's explanation. Here's the thing, I don't really care. It's like, listen, he pointed this out. I looked into it. I'm like, this seems pretty amazing, or at least according to Wolfram Alpha. And you can argue over that. And Hans pointed out there was a rhetorical mistake there because they're literally just quantifying the mass energy as the electric charge that would be within the field volume, so to speak, there. So it's kind of a cyclic definition, but I'm going to stand by saying that, yes, the argument is circular via Wolfram Alpha because this is the thing that it seems to be calculating. If I submitted a ticket, I'm like, oh, well, why is the case? This seems to be doing this. But it does seem to give, at least when you substitute for x here and you're trying to solve for the radius. So basically if you did, so it equal to h bar, and you were to just solve for x meters. So we can do that. So we're solving for a variable. We're solving for x. This is going to be in meters. Because that's crazy number right here, and that's in meters. So we added the unit. Oh, look. This appears to be precisely the classical proton. My question is, how long have they had the classical proton radius? Just because if this is basically just a mass energy conversion through some form of electric charge, when you actually divide by the fine structure constant to get the number that it represents, where is it? No, it's still off. It's okay, never mind. I'm hot garbage. Oh yeah, it's off by a factor of 4. So you gotta. Basically, it'll give you the 8.7 femtometers. Is that? Huh? 4 times. No, not 5. I'm sorry, I'm reteaching myself. It's been a little while. There you go. We get our 8.41 femtometers and everything. Why is that the case? I don't know. Apparently this is a known thing. So I'm just saying that this is a method that maybe there's some there. At least for the electron, I think it does. I think the electron is the one where it's just straight up the same thing. So if we go back, so we just go back, speed of light. Let's do electron mass. Keep everything the same. Okay, I think that is the classical radius. That's meters. There we go, that's the classical electron radius. Is the proton 4 times that? I don't know. Apparently that's a thing. I'm just saying maybe if that happens to be a known thing, it can calculate something that I think if we've had the mass and we knew it was 4 times, couldn't we have calculated this before we had actually done the measurement? I think there were some people that I think there were 2 papers that I found with this, and I think one person was in their 80s and didn't respond, and I totally forgot to send the other email. So that's my apologies on that. Okay, so I'm just saying if it happens to be set to the unit of action, that's kind of what, at least to my knowledge, and again, I'm not saying I understand quantum mechanics. It's like, all right, we're quantifying some stuff, they're doing some things, we're trying to explain it the best we can, and H-bar seems to be really important. I'm just saying if we had that value before and we knew there was a 4, couldn't we have just predicted the 8.4 femtometers or so, and now we've got a bunch of extra digits? Because if there was some there, that's a falsifiable prediction. So, hey, take it for what it's worth. Again, as I think Professor Keating said at one point, I pretend to be a science person on the internet. But, let's see. We should talk more, Kali. Listen, I can speculate like it's nobody's business, but we try to keep the speculation reined in. Just keep ourselves. I think Professor Wolf, one of the big things they're trying to do is they're trying to do bridge essays to connect things that might be from Wolfram physics to things more within more well-known mathematical physics, and try to find anchor points, so to speak. And who knows, maybe my project might go to help doing that, because you actually just go to Wolfram Alpha and you type in the terms that they were saying anyway, and you get the Planck power for a maximally entangled observer, whatever that might be, which it's the old noggin a jogging. Let's see. Times 2 pi. Okay, so a circle. Certainly. Hey, Lucas. Hey, yeah, Lucas has did an interview with Professor Wolfram over on his channel. Hold on, I got it somewhere. I put it in a community post. Hold on, let me find that thingy for a second, and then we'll just jump right back into this. Where was that channel? Hosts. Okay, so there we go. All right, so anybody who wants to check that out, feel free. It's over there, and we should have some folks from the summer school coming on to do some project presentations. I know some folks are probably going to talk at the upcoming Wolfram Tech Conference in November, and there's already a couple of things scheduled for the Wolfram Institute for folks to do some talks there. So, welcome, Bill. We may or may not have just been referencing some stuff and things, and that's why I love it. There's so much overlap and everything. But okay, let me go back to Dr. Unzicker. Hey, Upcycle. We're just getting into the meat and potatoes, so to speak. I know. 20 minutes to get to a point. Oh God, that was gonna be like my original project meeting with Stephen Wolfram. It's like, put together this thing, I was gonna argue, and I know I would have just rambled on for 20 minutes. Instead, he sat down, I have never seen Stephen Wolfram so concise as when it came to project assignments and stuff. It was like 12 minutes. Here are the things. I still had a little bit of back and forth, and then was like, oh my god, maybe I could actually do this. Hey, will we find something interesting? Probably not, but every once in a while you... look, maybe there's something interesting. Who knows? So let's get back into the discussion from Dr. Unzicker. So as we can see, we saw some of these equations. He had showed some of these before. We may or may not have put an whole earwig in there that's like, oh, well, maybe if you include some alpha or something there, maybe you get something interesting. I don't know. I think that's kind of interesting. So let's see what the good doctor has to say. We're sharing? Okay.
Should have started maybe with this one, so going the other direction, but you're all trained in mathematics, so you know what in both directions the equivalence means, so just walk back at the end. So I start with this coincidence, and it's really a strong coincidence. Speed of light, mass of the proton, radius of the proton, times p half is equal to Planck's constant that holds within the measurement limits of 0.84 femtometers today. So what you can do...
So the interesting thing is, since it does give you at least the first two digits of Planck's constant, and this is h not h bar here. So, the 2 pi, okay, yeah, that's what Rick was talking about. Okay, all right, that makes sense. I was going to say, just because you just divide that by 2 pi, and then if you had 2 pi squared, blah, 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 2, it's, okay, I think. Okay, the 2 is there, and I'm sorry, I'm still a little, maybe that was not exactly what he was saying. Okay. Doing great in 20 minutes. Hey, listen, the only reason I'm able to do any of this is because of the sum total of all of humanity. There's a whole bunch more smart people. I'm basically just a monkey with a magic typewriter and some smart people that told me places maybe to look. That's all. But okay, let's continue. So the claim is you get this, and if you get the first two digits of Planck's constant, it's look, it lines up with the first two digits, which is basically the only real certainty we have with the proton's radius right now, because it seemed to shift about 3%, which doesn't sound like a lot, but when you're talking about, I don't know, like 10 to the minus 16 for your orders of magnitude, yeah, that's particle physics, that's kind of a large amount. Okay, so H is, so H bar with a proton radius, you have a circular orbital speed. Okay, that makes sense. All right. Let us continue.
Is so okay, we multiply by c, you end up here, and then you introduce just the definition of the...
so he's multiplying by... Okay, I'm seeing. Because I was listening to this a little bit late last night. Okay, so he's got c squared there. So that means, look, you can do h bar c. That's... At least according to Wolfram Alpha's interpretation, that's bending stiffness. Whatever that might be. Perhaps it's important. We continue.
Of defined structure constant, let's assume that some genius is able to calculate that number.
Wouldn't that be great?
So you just put that 137 in here, and you end up with something like the electric force here, and then the rest of the equation is here. But then you, multiply by the electron mass, divide by g, and multiply, most importantly, by the gravitational constant, which...
To be fair, I'm still going through this, and I think... Okay, so he's got h there instead of h bar, because... So that would have an additional 2 pi. Okay, so that... Okay, I'm sorry. Yeah, that makes it 4. Normally, you'd have elementary charge squared 4 pi h bar c epsilon naught, or the electric constant there. If you just do that, that's just that with the 2 pi in it. So with that factor of 2 there, you get the 4 pi. Okay. I'm sorry, I didn't zoom in this. Okay, I'm parsing it as we're going through. So this is... I mean, this is stuff I'm actually kind of capable of doing. That kind of went over it with me. I sat down with Rick, and eventually you end up with something kind of like this. It's like, wait a second, these are obvious things. Let me just put them down and just look at them again, because I don't know, maybe you get insight, even through occasional chicken scratch. But I digress. Okay. So what have we done over here? All right. So you're moving that up over there. Okay. So you're getting 1 over that. Does that equal that? It might. Oh, let me just check. 137. Hold on. 137. Well, at least 3 digits. So 3 charge divided by 2 epsilon naught. Yeah, 2 epsilon. So divided by 2 electric constants. All right, I'm gonna bracket that. Oh, elementary charge squared, because it's going to be 2 things, so we need to get the charge out. Oh, yeah. Oh, that's neat. Yeah, it does give us bending stiffness. Okay. Yeah, so I guess it's at least 3 significant digits. I am over here. You can feel free to trust but verify. It gives you point like 997, something like that. So, oh yeah, it's about 2 pi. So at least for the first 3 significant digits. Okay, cool. Sorry, I am in the other screen, but I just trust but verify. Okay. So now we're introducing in. Where is that? Okay, so it goes to c squared. It gets to.
Which is, if you follow the Mach-Schermer hypothesis, something like this. You know, I have replaced the sum here by the mass, so this 4 became 6. You might also argue that's not 6, it's.
So I'm wondering if that 4 has to do with the radius of the proton, because that's kind of the thing that he's going in there. If that 4 becomes a 6, because that's a factor of like 1.5, or where's it come from? Let's see there. Okay, so he's getting g and pi. Okay. Should probably zoom out a little bit more. I'm sorry. Let's continue.
It's 1.5 anyway. We're just talking about numbers and orders of magnitude here. But you end up with this one, and then you can cancel a couple.
Okay. So we got c squared, big G, mass of proton, mass of the electron, and radius. Oh, sorry. Oh, good. I realized taking that out probably ruined my audio. Hold on, let me make sure. The audio is still, because AirPods, and oh, of course it's supposed to work for a Mac. Okay, I'm using my microphone. There we go. All right. Let's see. Let's see. Bill is commenting, was it the extended degree of freedom formula that he has developed? Photon term, energy of photons being laid is object radius divided by 137 natural log of pi. Squared over ln of 3. Okay. I remember saying that. I'm sorry, I absorbed so much, Bill. I remember going over it with you and everything, and I just remember what was it? That surface area thing where it's like, if you plug it in at the surface area of Earth, it's approximately the surface of the Earth is literally at like the magnitude, at least within that system, of h bar. I'm like, why do we live in like the magnitude of action that literally seemed to be right at the Earth's surface, or maybe just a hair below sea level? Which, I don't know. I thought that was interesting, because I'm always looking for connections, and if I can see something that looks like something else, I'm like, all right, mental note there. I might not remember what it is, but I at least have the concept that that's a thing. So that's pretty cool. Let's continue.
Couple of things here. Cancel C, you end up here. So we have something that already suspiciously looked like the gravitational force and the.
Okay. So, and again, I'm not necessarily sure the significance here, but I'm just like, all right, he basically ends with the mass ratio between the proton and the electron, which is like 1836. You divide that by 137. That's an interesting thing. Now, it's interesting because when we get to it, some folks are like, "So where does this come from? Like, what's your theory behind this?" And just like, no. This is just a recommendation of framework. It's all up to you to figure it out, which is fair. I don't know. Maybe Thad's conversation with a good doctor carried some weight. I know they were having Unzicker had gone over to Thad's poster. They were having a great discussion, and I realized, I'm like, I'm going to leave these two gentlemen to it. I have no need to interact with this. I'm going to go do my own thing. Just let them have their conversation. It seemed to be a good conversation from what I overheard. Long story, I think Unzicker's biggest objection was the whole, it's like, all right, dividing Planck mass by kilograms, because at that point, that would mean the kilogram was like, there was some reason, like they had some significance. It's like, well, these are just arbitrary things. It was originally, but technically the grade, which was based upon like a deciliter of water and stuff like that, which coincidentally, a cubic meter of water is really dang close to like 1,000 kilograms within a meters. So that's just an interesting thing. Now, why would water be important? I don't know. It seems to be important. Hey, at least it's important to me. I'm like 80% water. I tend to go the path of least resistance. And Shiloh kind of made an offhanded comment one day. It's like, the sun's basically like the density of water. And it's like, that's interesting. It's like 1.4 grams per centimeter. Water is basically 1 gram per centimeter. Or with a pinch of salt, as I think Rick has said before, a pinch of salt at the right temperature and pressure, it is precisely 1. Another thing I got out from the units project is, again, I can do some calculations, but I'm like, how the heck do I justify this? And I've been trying to grasp for straws. The two things are either one, maybe there is something magical about water. I don't know. It seems to be a fascinating substance that seems to have very interesting properties. I had interviewed Michael Hughes before, Dr. Michael Hughes. I still need to have him on to continue our discussion about water and all its fantastic properties. The other interesting thing is Professor Gerard Utuft had mentioned that the Planck momentum, I think is either him or somebody else said, once you have momentum, you are cooking. The interesting thing about the Planck momentum, it is like 6.52 kilogram meters per second. At least within the magnitude for observers like us, given our system, it's magnitude 1. So part of me is like, well, if the Planck momentum is of our magnitude, maybe we just kind of got lucky. Maybe we got lucky for other ways. I don't know. It's but it I don't know. It is very interesting that it's like these things seem to work out. You could always make the lazier argument and just say it's like, well, if the Planck mass is to be meaningful, the kilogram needs to have some meaning to it. If you don't believe the kilogram is meaningful, then the Planck mass is expressed in kilograms. So you could make that. That's not the most satisfying argument. You're just kind of arguing and trying to like, I don't know. I prefer it's like, you lay out the case, and if it's so obvious, you're like, you don't have to agree. But if your argument against it, like, don't hold water, then maybe there's a pun there for us. So let's see. Where are we? Okay, let's continue. Both displays. Oh, well, volume does go up. Every radius you go up for like a sphere or something like that, your volume is going to increase 8-fold. Because if your square volume, area goes up by squares, volume goes up cubically. So if you go for radius from 1 to 2 and you square it, you're going to get 4 for surface area. But you need a cube 2, it's going to be 2 times 2 is 4. times another 2 is 8. So you can have a magnitude of 8 difference. See, that's the thing. And I know a lot of folks, they have a lot to say, and you see a lot of calculation. And I remember there was something very interesting about that. My thing is, I'm a simple dude. I just work in Planck units, just because it's like literally 1, and then you can just scale up from there. The 16 pi factor for the area is an interesting thing, though. So I digress. And technically, for Schwarzschild, you always have to have 2. Why is that? I don't know. Again, I could speculate, but let's continue with the argument here. So we're putting these in. Okay, so he's putting c squared. Hold on. Let me go back. Let me put this guy in because I have not done that yet. So let's go back over to a window here. Okay, so okay, here's the calculation from the other thing. You did that 137e. So as you see, it's giving you the Planck constant speed of light product, which was essentially 1. That's based on the first 3 digits of 2 pi. We threw in 3 significant digits there. Okay, so let's open another. Okay, so what do we have over here? C squared G. All right. C squared, big G, proton mass, electron mass, and proton radius. Why aren't we including the electron radius? I don't know. I'm gonna just free falling. Radius. All right. Multiplication. Okay. Well, it's not giving me. Okay, there's something. What do we do? Let's try the classical. Hold on. C squared is okay. So C squared, speed of light squared. Big G is Newtonian gravitational constant. Check. Proton mass, electron mass. Proton mass, electron mass, classical proton radius. Oh, we use the other one too. I mean, what is this trying to... I'm not sure exactly what this is trying to come out to. I mean, I don't want to be negative because this kind of looks wrong. Or at least it's... Yeah, I think... Oh, I think you need to divide them. Is there a divide in there? Okay, well, let's just do that. Let's see if we can't make it right. Because even when I was at Eric Lerner's thing, he had some calculation looking. I'm like, I take it. I'm like, all right, this is just wrong up by a order of magnitude. Oh, look, he just forgot to inverse this. It's like, listen, I can be critical of folks, but it's like if someone just made like a very simple like clerical error or something like that, I know what they meant. Especially if it comes out like pretty close to what they're saying. So, all right, proton mass. Let's divide. Let's see. This gives us something interesting. Oh, I shouldn't put a period after that. Okay, multiplication. Okay, that didn't seem to help. I mean, okay, so this might be equivalent. Okay. Let's... I mean, this is kind of annoying. I mean, again, I'm not a mathematician. Shiloh and Anastasia like to refer to me as a mathematician. Again, flashbag magic typewriter where I just type in some magic words and occasionally some actual digits and stuff. Okay, maybe these don't need to be equal. Let's do that other thing. 137 elementary charge squared. Okay. And then let's just do pi electric constants. So we'll do this. Pi. So I want to see this. Again, I'm very biased. Again, it's like, it looks like he did a little bit of synthesis. And again, it's maybe I had nothing to do with this. Again, I'm superimposing because of my own personal narcissism upon this. So, all right. So c squared radius of universe. Okay. So let's do this. All right. So c squared radius universe and 6 mass of universe. Alright, so alright, and then I'm going to divide that by 6 mass universe. What's that other factor we had there? Mass of the electron. Okay, let's see what the heck happens. All right, bracket that. Bracket that. Let's see what this gives us first. Let's see if it even gets us far enough. Might need to retype those terms or just put them in manually. Oh. This mass element. What? Okay, we confused it. Let's just do this. Put this over here. We'll calculate this separately. Observable. I knew it. I knew it. I tried to cheap out. I tried to cut corners and computationally reduce it. It didn't work. This should... Oh my god. Okay, let's just do this. This is annoying. Radius. Oh. Read! There we go. Jax, that's a good question. That's a good question. How is time treating me? Well, I might be treating us all in a very fair manner, so to speak. Of course, I just needed to put it after. Okay. So, observable universe. Observable universe mass. All right. Maybe we'll like that one better. Oh, looky. Oh, hey, calculate. Universe mass is ordinary matter. Universe. Okay. Then we need to multiply it by the electron mass. Let's see what happens. Electron. So we get a mass in there. Now, maybe this is a constant of proportionality. I can't get it to work. Let's see. What am I? I don't. Let's see. Okay, I'm just going to take the electron mass out of there, and I'm just going to take the square root of this because I can. Because that'll give us. Oh, it's just going to give us acceleration. Because it's our gravitational acceleration just without a mass. So square root. Because it's going to lower the top one to 3 lengths. And then the bottom will have 2 times in it. Just because we're dividing it. Oh. Look. Oh, looky. Standard gravitational. Oh. So 2 times 10 to the minus 18. That's interesting. That's It's kind of reminding me of Dr. Mike McCulloch's quantized inertia. Why does he keep on finding 2 to the 10? I think it's only meters per second squared, so I don't think he has the 3 derivatives in the top in the length there. Why does that keep on popping up, and why does it seem to potentially provide an explanation for that dark mass effect, or whatever that might be? I just know this calculation is really dang close, because I can get like 1.453 or something like that when I throw in the Planck stuff there. And okay, that's interesting. Oh, that's in kilometers, but that's 10 to the minus 27 is the mass parameter of, or at least the magnitude of the proton. So, okay, I can't verify this. I really wish this. Is it about the same thing though? I took. Hold on, we need a. Hold on, let's go back. Back. Electron mass. I'm trying. It's okay. Speed of light square, Newtonian gravitational constant, proton mass, electron mass, mean charge ratio. Okay, the radius of the proton. Oh. Okay, this should give us big G then. Okay, wow, I was just skipping ahead. I apologize, Dr. Unzicker, I think. So give us at least a gravitational proportionality of something. Okay. Oh. It's giving us basically a gravitational coupling, except mass isn't. Oh, that gives us bending Oh. I said these things, but now it's kind of sinking in a little bit more. Very cool. Which does it different from Big G? I mean, Big G is in there, so. So, infinity, blah, blah, blah. Okay, we got some radicals in there. We got some radicals. We got a 3/2. I can't parse it right now. I'm sorry. It's, uh-oh, gotta get the kitty. Well, Jax, hopefully, things start picking up there. It's, I mean, I ain't the boss anybody, but hopefully, things will pick up. I know it's tough for a lot of people. Okay, so we've got that. Let's times the. Okay, so let's just do this. Let's go back. Let's just add that mass of the electron here, because apparently that did wondrous things. So, what was the last term? Mass of the electron. Okay. Wait a second. Mass of the electron on that side. Wait, did he have that over there already? Okay. It's that 137 thing here. So 137. Okay. Electron mass. Okay, negative. Okay. That seems to at least be a little closer, I think. I mean, I don't know what to tell you here. I mean, this. Do I have the pi? Pi, electric constant, speed of light squared, radius of the observable. Maybe he's using the Hubble things, because I would adjust it a little bit, but it shouldn't be off by meg. I don't know what to say. I don't think this is correct. I'm sure there's something here, but it's just at least putting it in Wolfram Alpha. Again, maybe just Wolfram Alpha's getting it wrong. C squared, radius of the universe. C squared, radius of the universe. And then there's that 6 universe mass. I mean, even if you added in like the other, whatever, 25 or... Yeah, it's not going to be 30 orders of magnitude. I think there's a clerical error here. I'm not going to... Let's continue listening. Wow, I apologize. I'm slowly getting... Alright, let's continue. Hold on, I need to... Sorry. I need to actually share the audio. Hold on, let's do this. Go on tab, and... Here we go.
Something that already suspiciously looked like the gravitational force and the electric force here. So what you do is the electric force and the gravitational force times these cosmological quantities have something to do with the radius of the proton, or eventually you see that very naturally, if you assume this to be true, then you very naturally get the ratio of the electric and the gravitational force by these two quantities. That's 10 to the 80, and these two are 10 to the 40 in the denominator. So you have this factor of 10 to the 40 or 10 to the 39. You would have explained this, okay? I'm not saying anyone has done this. I'm just claiming that this is the way, as a big picture, we need to follow if we somehow manage to calculate the 137 and 1836, then we would have demonstrated the equivalence. It would make much sense. And I think this is a much more intuitive and insightful formulation of that Dirac's hypothesis. And this is maybe the formula we...
So, all we need to do is find somebody that can figure out what the heck's going on with the fine structure constant and gravity. I mean, that sounds like a pretty big ask, but hypothetically, if we happen to find some folks that could have a coherent framework that seems to be able to explain more with less, maybe we can figure out what's actually going on. I think that's the goal, right? That is the goal. See? That's the goal. I wrote it there, so it must be true.
Would have explained this, okay? I'm not saying anyone has done this. I'm just claiming that this is the way, as a big picture, we need to follow if we somehow manage to calculate the 137 and 1836, then we would have demonstrated the equivalence. It would make much sense. And I think this is a much more intuitive...
Correction. That was a baño break. I still have a little coffee left to run through the system. Very good insinuation, though. It lines up with past history, Jack. So that's fair. Where are we? I was really hoping these would come out a little bit better. I might have to send Unzicker an email and just let him know that it's... Again, there were some math folks there, so I'm sure folks let him know after, because everybody has little mistakes. Heck, apparently there was one of the Rock's papers or something from back in the day. It was only like 7 or 8 pages long, but 2 of the pages were out of your order for like 40-something years before anybody actually said something. Now, maybe people noticed, and they're just like, okay, well, this is a thing. Or maybe it was just so dense, and or not a huge amount of people read it that nobody said anything. So that's one of the things, because it's like, just because there's no known answer out there doesn't mean that somebody hasn't figured out something very intriguing. So that's kind of the MO that I work with. It's like, if people say this cannot be done, And then someone showing me something, it's like, well, this can be done. Okay, people say you can't calculate this. And then somebody shows me that they calculated it. Now, you can argue about how they calculate it. You can say, okay, well, this isn't correct. Maybe there's nothing there. Like, dividing by kilograms is it's just a random thing. It's not like the kilogram is fundamental. I mean, you would have to say maybe the Planck momentum has some fundamental being on our level just because it happens to be magnitude 1 for where we're at, or maybe, I don't know, maybe we just got lucky with the meter and North Pole to Paris. No, excuse me, North Pole to the equator by way of Paris divide by 1 million. I would insinuate that maybe there's something significant about the Earth, or maybe we just got lucky because we based it on a deciliter of water. And again, you would need to have a fundamental method for explaining this and showing why that would be the case in some way where people just go, oh, that makes sense. Now again, like Dr. Unzicker, it's like, I'm not saying that somebody has done this. I'm just saying that I think humanity, it's within our ability to probably do something amazing like this. So, yeah, okay. Jackson's commenting, it's not about being right every step, it's about showing the work for others to pick up. Exactly. Showing, yep, exactly, Bill. That's what it's all about. It's like you look at things, you're like, oh, that's interesting. You go through, it's like, well, that's not supposed to be there. It's like, all right. One of the biggest things I learned from that, it's like, what if I assume this was true? Let's explore it. Sometimes it goes absolutely nowhere. Other times it may lead to very interesting results. So let me do this easy one. Saying the force electric and the force gravitational, summation over the mass and then over the radius, blah, 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 blah. Okay, let me just do this real quick. Just to be fair, I don't think I've ever actually done this. 1836 divided by 137. Maybe I did do this before. Sorry, let me share. Okay, factors. What's this? You tell us anything interesting? Not really. And again, those aren't the exact numbers. Okay, so hypothetically, I think he had runs the interval. What is it? It's mass of universe, radius of universe. So sum all those. So hypothetically, let's just do. Don't mind me doing meters squared over length. And then divide by no. Yes, as I'm pulling numbers out from my butt here. Yes, 8.3315 times 10 to the 61 kilograms. Yes, don't mind any of my nonsense. Wait, was that supposed to be equal to or force electric to source gravity? Okay, so that should be like a 10 to the 39 number. Huh. Okay, so I get 10 to the 28 kilograms per meter. Okay, so that's a lot. I realize I'm not running the integral and stuff like that. Let's just do the normal thing. Let's do the observable stuff. Universe. No, you go here. Universe mass. I mean, that is an interesting. Okay. Where is that? That is electric force, gravitational force. Let's just do this. Electric force by gravitational force, and again, they're equivalent of the Planck length. Okay, so they're just showing the force, Newton's. Okay, that's. I should probably. I need to express the magnitude, don't I? I'm not asking the right question. Okay. So let's just wrap up with a few last comments from the doctor. I'll try to play around a little bit more, see if I can see what he was trying to say, but it just doesn't seem to quite line up. It's again, maybe I'm just. Okay, let's go back to the window. Hold on, c squared over 4g. Let's do that. That's an easy thingy. So anything interesting? Then you would sum that over the mass and then length. But oh, it's supposed to be the distance between things. Okay, that's why it was off. All right. Unit. Okay, linear mass density. I mean, okay, that's what do you have? Okay, so that would be when you run it over the sum of all mass in the universe and all the distance between all the mass in the universe. So, okay, I mean, maybe I'll give it to you, but I don't know. I couldn't get it to work. I apologize. Let's just wrap up with
intuitive and insightful formulation of that Dirac's hypothesis. And this is maybe the formula we should work on and try to explain on a very microscopic level. So this is...
So if I'm not mistaken, this might be exactly the Zitterbewegung radius formula.
Yeah. Because, I mean, then you can go ahead and assume that, okay, let's speculate about if you have a circulating light wave or something like that, and you end up with that. But you agree that maybe this is the intuitive stuff we should try to work in instead of just wrecking our heads around this crazy coincidence of with the cosmology.
I think the strength of the charge force actually does increase as the radius gets closer as well, because that's the thing. Electromagnetism is supposed to have a pretty strong effect, and then but the thing is with gravity, it starts going up really fast as you start getting closer and stuff. So, but they do, if you do what is it, Planck mass times the Planck mass divided by the Planck length squared or whatnot, and then you multiply it by big G, you're going to get the Planck force. And then when you do that with Planck charge, Planck times Planck charge divided by Planck length squared, and then you multiply by Coulomb's force, you're going to get the Coulomb constant, you're going to get the Planck force as well. So it's like, I mean, Jonathan, somebody was asking me about that before when I had Jonathan Gorado on a few years ago. He's like, it's basically the same equation. You just have a different constant. But it's like, is there a connection here? Meh. People say no. A lot of folks have said yes. Maybe Kaluza-Klein, because it kind of links that up in 5 dimensions. But Bill is saying that he means a object radius from multiple particles. Gravity of a large black hole per Planck area is lower. Yeah. Oh, that is interesting. Why? I mean, these are intriguing thoughts.
Theoretical derivation of this
No, no,
So that's what
no.
that was my impression with the
No. I don't have. I haven't given it a theoretical derivation. That's your job. For new.
there might already be one there.
No. I'm just saying that this is equivalent, or more or less equivalent, to Dirac's large numbers, but it's much more intuitive if you want to go beyond. But
Okay. So apparently people are asking about the derivation. It's like, oh, no, I don't have a derivation. This is just an interesting way to think about it. I agree. If only somebody has gone through and maybe done some work to help derive this and or look at these relationships. Because I think these are interesting relationships. Maybe I just made a mistake. I'm sure I probably just made a mistake somewhere. Oh, hold on. Did I not square elementary charge? That's probably what it was. No, I squared elementary charge. Okay, never mind. It's probably just a clerical error in there. The general concept, I think, is very intriguing, and we shall see where it goes. But gravity, yeah. So if it's putting out a Planck energy worth of gravity, that's about 10 to the 9 joules. Yeah, and then it's 4 pi Planck area over there. I think. Oh, okay. So yeah, over there. Yeah, so that's 1 order of magnitude. Okay, so that makes sense. All right. Because you multiply, you'll get up to 10 to the 9 joules. So okay, cool. So I mean, this was intriguing. I guess maybe I was wrong about. Have to check some of the algebra and everything and see what it's actually supposed to be. But this was an interesting jaunt, and especially if you have occasional interactions with folks. And again, I'm not saying that any of the emails or conversations that may or may not have been had influence some of this, but it's I don't know. It's fun to talk about these things and see other folks and how we may or may not affect them, or as Bill might say, entangle different interesting folks together and see what happens. So that's all I got. Oh, hold on. That's the wrong thing. Leave the studio and just keep the show running. Why not? But yeah, that's all we got for right now. So other than that, just keep up the good grind, and we'll see what's going on, and hopefully have a bunch more interesting folks on to share some really cool ideas. So until next time, everybody, take care of yourselves. It's a wacky and wild world out there, but let's hoping for a better tomorrow. Peace out, everybody.